Dear scientists, doctoral candidates and students, dear colleagues, it's a pleasure for me to welcome you today to the 10th International Excellence Talk of Karlsruhe Institute of Technology, KIT. And I will also send you warm greetings from Professor Thomas Hirt, the Vice President for Transfer and International Affairs at KIT. This lecture series was initiated exactly 1 year ago in May 2022, and it is designed to provide a platform for exchange between researchers with internationally renowned colleagues in an interdisciplinary context. And we are very glad to cooperate with the Humboldt Regional Group Karlsruhe Pforzheim. We have invited them to a series alternately presenting Humboldt Fellows and awardees at KIT. And today, I'm very happy to introduce Professor Dr. Yuri Estrin, Professor of the Department of Materials Science and Engineering, Monash University in Melbourne, Australia. Our today's speaker is an international authority on materials science and engineering, particularly in the areas of physical metallurgy, materials modeling, and development of new materials. He's a fellow of the Australian Academy of Science and a holder of numerous international awards and prizes, among them the Humboldt Awards in 1999 and 2012 and Helmholtz International Fellow Award. Dear Professor Estrin, I'm looking forward to your talk today and will be happy to personally welcome you at KIT at one of our live events in summer. And now I would like to hand over to Professor Thomas Bölke, who will give a short overview of the academic achievements of Professor Estrin and briefly introduce highlights from this successful cooperation.
Thank you very much. It's a great pleasure to give here a short introduction to Yuri Estrin's CV and to the research highlights. Professor Estrin studied physics and materials engineering in Moscow, and is today, as already mentioned, one of the most cited scientists in the field of physical metallurgy and materials modeling, especially in connection with dislocations. And he also made significant lasting contributions to the development of new materials. He worked as a researcher at the Institute of Crystallography of the Academy of Sciences of the Soviet Union and received his PhD there in 1975. He habilitated at the Technical University of Hamburg-Harburg and became a professor of physical metallurgy. In 1992, he became a professor at the Department of Mechanical and Materials Engineering at the University of Western Australia. But then from 2000 to 2008, he held the chair for metallurgy at the Technical University of Clausthal in Germany. And it was exactly in this period that I have had the honor to give a joint lecture to the students there in material science and continuum mechanics. It was really inspiring collaboration and teaching. After the time in Clausthal, Yuri Estrin moved to the Department of Materials Engineering at Monash University in Melbourne as a professor and later as a director of the Center of Advanced Hybrid Materials. He's currently an honorary professor there. Yuri is the author of more than 500 publications on nanomaterials, alloy design, thin films, hybrid materials, and multi-materials, and the design of nanomaterials based on geometric principles. And Yuri Estrin is also adjunct professor at the University of Western Australia and the Nanjing University of Science and Technology in China. He's a fellow of the Australian Academy of Sciences, and he was in 2015 awarded the Thomson Reuters Australian Citation Award. In the KIT Future Field project, accelerated design of interface-controlled advanced materials by simulation-informed experiments, the application of a Center of Excellence is currently prepared. The speaker of the team is Martin Hallmeier. And as part of the research activities in the preparation of the proposal, we collaborate with Yuri, and especially in the field of nano and micromechanics, the mechanics of dislocations and multi-materials, in order to a network in the group and to extend the network on an international basis. Additionally, the ongoing collaboration between Yuri Estrin and Peter Gumsch and Horst Hahn on architecture materials will be further developed. And this was only a very short overview, and it's really a pleasure for us all here to have you as Yuri here in Karlsruhe. And it's a great pleasure to attend your presentation. Please, the stage is yours.
I'm very glad to be affiliated with KIT. I also quite happy that the Gesellschaft der Humboldtianer is part of this series, as I owe the Humboldt Foundation quite a lot, even personally, not only scientifically, but personally. It's a wonderful institution. I'm going to talk about something that evolved over the years and is part of my collaboration with KIT, not so directly perhaps related to what I'm doing now with Professor Thomas Bölke. This research is, well, in the middle of progress, and it's perhaps a bit too early to talk about it, but the subject that I'll be presenting today appears to me to be of somewhat general interest, and I thought I could share that with a broader audience. I'll be talking about somewhat disparate subjects because there are different approaches to architecturing materials to provide them with a internal structure at mesoscale that makes them so interesting, that perhaps even defines their mechanical and other properties more than their chemical composition or phase composition. So there are various ways of manipulating this intermediate mesoscale structure, and some of them will be covered in this presentation. I'll touch upon biomimetics and bio-inspired materials. Then I'll move to lithomimetics. It's a new term, and I'll explain what is meant by this. Heterostructured and harmonic materials is another group of materials designed with a particular inner fabric, inner architecture that gives them interesting properties. I'll dwell a little bit more on topological interlocking materials, a subject that occupies my thoughts quite a lot. And if time permits, I'll also talk about architectured lattice materials. This is an area of research which is very strong at KIT. Professors Peter Gumsch, Professor Gumsch and Martin Wegener are champions in this area, and I think you heard a lot already about this group of materials. I'll see whether we can talk about this today or not. Some of the ideas and views that I'll be talking about have been already presented in a book that appeared recently, Architectured Materials in Nature and Engineering. So we'll be talking about nature and inanimate nature in particular, and well, let's see how we go. One can blend different materials within a structure in many different ways. And as I said, if the shape and spatial arrangement of the constituent parts of a material become the main feature, the new degrees of freedom that enlarge the design space, then we can talk about them as architectured materials. We call them archimads, as for brevity. In the American literature, these materials are called architected materials. And there is obviously some meaning to that. Not only are they sculpted or architectured, but they also have these materials I'll be talking about, have some aesthetic appeal. So this connotation with architecture is perhaps quite appropriate. Here is one example of a structure which is quite common in nature, the so-called Bulligan structure, and that shows how material one can be arranged into fibers, the fibers arranged into a layer, and a second material is designed similarly, but then you alternate these layers of materials 1 and 2, and you twist the structure so that you get some sort of a plywood structure, Bulligan structure, as they're named. That is just one example. This structuring or architecting can be done at a mesoscale, say in the millimeter or sub-millimeter range. Here on this logarithmic scale, one can talk about nanostructure, microstructure. Here, the macrostructure, that is already an engineering part, structural member. Our architectured materials sit somewhere between this macro scale and micro scale, and that's where we will see the major advantages of this architecturing. Now, biomimetics. In living nature, there are magnificent examples of complexity produced from very simple ingredients. And in fact, the number of chemical elements that make up living structure, living matter, is very limited. You can see just 8 here, the major elements. In engineering materials, you have a huge palette of materials that you can use in alloys, in various composite materials. And of course, the way in which engineering materials are produced are quite different to the way in which biological materials are produced. Biological matter is produced by growth, and that growth occurs at different hierarchical structural size levels. These structures are very adaptive. They can remodel in response to external conditions. They can self-repair, and so they're very versatile and efficient. So it would be good to have this with engineering materials. But engineering materials are rigid in many ways. They are produced by forming or powder compaction or producing solutions. They are very difficult to recycle because there are so many elements which are combined in an intricate way, and separation is difficult. So in the new era into which we are moving, it is certainly a big problem dealing with this complexity of the chemical composition of the material. But of course, that gives an engineer the possibility to select from different materials depending on the design specifications, and there is a very good way of predicting the properties of such materials and doing engineering calculations that gives some secure designs. So there are pros and cons for this traditional engineering approach, but one can beat this rigidity of the traditional approach by combining elements of just a limited number of materials in a structure that gives us this architecturing, which also gives us a way of easy separation of these materials for the sake of recycling. And I'll be talking about a bit more during the talk. An example of a biological material. It's the structure of a cuticle of a spider, coming from the paper by Peter Fratzel and colleagues. the building block here is just a single fibril combining chitin and proteins. They are aligned in this way in the plane. They can be those planes layers can be stacked together in a simple way, but they can also be stacked in a plywood way, Bulligan way, and then intermittently you put elements of such structure, unidirectional array, and Bulligan structure, and this design gives a fantastic combination of mechanical properties, a huge strength and also a very good fracture resistance. Some example of a similar structure is the club of a mantis shrimp, which is perhaps unbeatable in terms of this combination of properties. The plywood structure also is encountered in bone, in lamellar bone, and if a crack propagates along the bone, it experiences oscillations perhaps, or just alternating layers of hard and soft material, or stiff and pliable material. And if a crack propagates along such a structure, in a non-lamellar structure, you can see it moves very in a straight way without any big resistance. In a lamellar structure, delamination occurs. The path of the crack is quite bizarre, and there is a high energy dissipation associated with that, so that the fracture resistance is strongly enhanced. So from this, even if in an engineering structure we cannot directly mimic this design, we can at least get the idea that having a lamellar structure and playing with hard and soft gives us great benefits. And in a simple example, we just wanted to demonstrate this in a standard material which is ductile, material 1, and hard material, ultra-fine grained material, which are usually strong but pretty brittle. That's the stress strain curve of this brittle material. And if you just take this brittle material and have one single layer of a soft material, you get, so the material 1 is ductile, the material 2 fails by strain localization in this way, the hot red areas here. But if you introduce just one layer of soft material here, you kind of diffuse the propagation of damage, and you get a behavior shown by curve 3. So it is not as ductile as 1, it is not as strong as 2, but the combination of properties is much more favorable. So it's tolerant to plastic deformation to some extent, and it has not lost a lot of the load-bearing capability of the strong initial material. You can also have a more complicated architecture, a complicated structure of the soft layers here, and by that you can further improve the performance of this material. So this is a simple example, and there are many where you can manipulate the material by introducing layers or other geometrical objects of a soft phase into a hard one. Another example from biomimetics is the responsiveness of the structures. Here, just a couple of beautiful pictures that show how, say, a pine cone can open or close in response to humidity. I'm not going too far into this, just wanted to show you some pretty images. But what one can perhaps say about biomimetics and its present state is that it has produced a lot of interesting ideas, but it has also produced the recognition that one cannot and should not probably directly emulate the structures from animate nature, but rather get some design principles like combination of soft and hard layered structures, spiral structures, which provide beneficial property profiles of materials. Now, that is something that one learned from bio world, but there is a huge inanimate nature objects and patterns, and they are no less interesting and beautiful than those of the animate nature. So what we tried to do in collaboration with particularly the Institute of Horst Hahn, Brigitte Beretsky, ENT, and a significant contribution there was from Anne Kulagin of that institute, was to look at a catalog of structures of inanimate nature, and we focused on the Earth lithosphere. One can see objects like vortices or this kind of structure, or a lot of layered structures seen here and here, the so-called chocolate boudinage structure. If you look at them, you can suspect that they may have some interesting features and possess some interesting mechanical properties. But we have no proof of that. It's just a suggestion from nature whether one could look for interesting design ideas and inspiration. Fortunately, there are experimental techniques in metal forming that can produce structures which are similar to those of lithosphere. The whole range of severe plastic deformation techniques, and some examples are shown here, produce those structures. One is the high pressure torsion, the technique where you deform a little penny-shaped specimen between two anvils under high pressure, vertical pressure here, several gigapascals, and you rotate those anvils. The technique goes back to Bridgman, and it's quite popular in the materials engineering community. You can produce huge strains of hundreds and thousands, not hundreds and thousands of percent, but really hundreds to thousands. So you can really, by this rotation, by this shear deformation that you produce, you accumulate a huge strain, and with this strain, you break down the microstructure of this material down to sub-micron scale and quite often to nanoscale. That means that you have a bulk material with very fine granularity, with very small nanoscale grain size. That provides the material with very high strength. You know, most of you would know that the strength of the material scales as the inverse square root of the grain size. And the grain size here being so small, you get a huge mechanical strength of the material. There are some other techniques like equal channel angular pressing, where you push a billet through an L-shaped channel. It comes out with the same cross-sectional dimensions so that you can repeat the process. You put the billet again and again and again into this die, and again you accumulate very large deformations. There are some other techniques like this one, the asymmetric rolling, where you can also produce large shear deformations. The twist extrusion technique, pushing a billet through this complex twisted channel of the die, you can produce, again, very high strength and very small grain size. Now, at ENT, the most popular technique is this one, high pressure torsion. And the structures that were produced are, for instance, like this one. You take two materials, you co-deform them together, and you obtain a rather complex structure. It is shown here as an idealized picture where you have two different materials. You do this high pressure torsion deformation. You break down the layers into a pattern of this kind, for instance. And if you continue, you go on and on, you could even get almost full mixing at the atomic scale. So that is something that would be desirable if you want produce an alloy by this mechanical alloying in the bulk. If you want to have a solid solution where normally by other melting techniques or other techniques, you cannot produce that structure. But you may, and in our context, you actually wish to have something like that. You want to stop at the right moment where your architecture, the inner fabric of the material, is of some interest if it promises some good properties. So this picture by Van Gogh shows you this sort of mixing and whirling. Now, what I should say is that if the layers are ideally matched and these lines are parallel to each other, no mixing would occur. But if you have some perturbations on the surface, or if you deliberately design the die so that you can plug into or plough into the material and mix it in a more efficient way, you can get a quicker and better mixing. Now, we did some experiments on the deformation of a layered material, just looking at three layers: copper, molybdenum, copper, soft copper, and hard molybdenum. This is the specimen deformed by high pressure torsion. Then, if you look at a little specimen taken out of here and look by computer tomography on the inner structure of such a specimen, then you would see that you have the greatest degree of chaos or turbulence near the ends of the specimens, near the edges of the specimens, that is here, where the shear deformation is the biggest. You get, of course, some mixing here closer to the axis, but it is more pronounced here. So, and then you can look at the structures and test the mechanical properties, or look into the microstructure of these intermixed layers. And what you will see is, let me just show you a picture produced by computer tomography that shows how this turbulence in the solid state occurs when you do high pressure torsion experiments in this molybdenum sandwiched between the two layers of copper. It's quite remarkable what happens here. Please note that the whole happening is in the hard layer, of molybdenum. So it gets fragmented, and if you look at the 3D reconstruction of the molybdenum layer, you will see that it is still contiguous, but you have some ruptures here, and those ruptures will be filled with the copper material, and that mixing will occur. Now, if you look at the microstructure, say here, look at this little element where molybdenum is marked here as 2 and copper as 1. And you look at the grain structure of copper and grain structure of molybdenum. You will recognize immediately that copper has the sub-micron grain size. The average grain size is sub-micron. Here the scale bar is 5 micrometers. Here it's 3 micrometers. So the molybdenum has the grain size in the micrometer range, copper in the sub-micrometer range, meaning that its mechanical properties are very good. It's very strong. So you get both things. You get architecturing of the material. You have a bizarre structure inside the material, but you also have grain refinement that gives you strength of the material. In computer simulations, mainly done by Alexander Filippov, this fragmentation of the molybdenum layer was modeled, simulated. The simulation was based on the so-called movable automata technique, which consists in, well, I'll just take an example from Salvador Dali's segmenting his beloved wife, Gala, into individual blocks. Now, you introduce an interaction potential between these blocks or particles and look at how these particles flow. So you simulate the flow of a gas or liquid or a solid by looking at the movement of these particles. It's not molecular dynamic simulation, it's a much coarser scale, but this technique is quite powerful and it gives you, indeed, it shows you how at different stages of the process you get this fragmentation of the hard layer. Now we have a tool with which we can try and predict what will happen in a multi-layered material when we deform it by one of the techniques that we propose. The microstructuring or nanostructuring that occurs simultaneously with the architecturing of the material opens up a way of downscaling the processes because this process actually produces pretty small samples. But in the technology of the future, with the trend to miniaturization, that is what we need. We need only a small amount of material for micro parts, for microfabrication. And there are some ideas of why microfabrication will be promoted by producing materials in this way. I shouldn't dwell too much on that just for the sake of time and move on to the next subject, the heterostructured and harmonic structure materials. Again, most processes give you a material which is non-homogeneous. So heterogeneity is intrinsic in the materials. But if it becomes a controllable inhomogeneity, if you can engineer that in a particular way that gives you the best properties, like producing layered materials with a coarse grain layer alternating with the fine-grained ones, thus changing periodically the strength of the material, or gradient materials from surface into the bulk. If you can do that in a controlled way, then you have a tool to design materials with programmable properties. The boundaries between such layers play an immense role because that's where dislocations get piled up. They cannot penetrate across the boundary. They can raise the stress in the adjacent zone to that level so that they produce a forward stress in the hard zone, but such a dislocation pile up also produces a back stress in the softer zone. And that gives you the so-called kinematic hardening, which enhances the mechanical strength of the material. So in this way, in this controlled way, several groups have design techniques to improve the properties by either bombarding the surface of the material with small particles, the so-called SMED process. This is surface mechanical attrition treatment. That's the acronym that stands for that. And at the surface of the specimen, you produce a hard layer with the grain size of, say, 100 nanometers. In the core of the material, you have the initial coarse structure, say at micrometer scale. And then there's a gradient layer, a transition between this layer and this layer. The hardness of the material varies, of course. For the hard surface one, it is in this range, and then it drops off to a low one in the soft core of the material. Now, if you measure the mechanical properties of layers of materials, if you slice the material like that and have miniaturized specimens and do tensile testing on those specimens, you get the stress strain curve for the coarse-grained material. For the nano-scale material at the surface, it would be a curve like that. And then there are some intermediate ones. And if you add up the loads that are carried by these layers using the so-called rule of mixtures, you would get, if this is the coarse-grained one material, you would get this green curve. In reality, in experiment, you get this curve, the red one. That is, you get much more than the additive contribution of the layers would produce. That is, there is some synergistic effect which is due to this gradient structure. And there are now various efforts to understand exactly how that works, how a gradient plasticity theory should be designed to explain this. But the experimental outcome is quite appealing. It is an increase of the strength of the material, actually without loss of ductility of the material. I skipped this slide, which shows another way of producing layered structures in titanium that give also a very good combination of mechanical properties. Just in order to have time to mention what happens in the so-called harmonic materials world. This is the work by Amiyama mainly and Dmitry Orlov in Sweden. They take metallic powders, in their case nickel, or in this particular case nickel. They do ball milling of this nickel so that the surface of the particles becomes hard and small grained, and the core remains soft. Then they consolidate this material by spark plasma sintering, and they get a material with a soft interior and hard shell around that interior. And the mechanical properties of the ultrafine grained shell material, which is like that, very high strength that you can see, and the soft one response of the core material in combination give you this curve. Again, good ductility, high strength. So that is an interesting design concept. But now I'm moving to the subject that I wanted to present at some length, but probably don't have time to do that at length. But I'll still want to show you the benefits of segmenting materials, particularly brittle materials, into smaller components and then reassembling them so that they would interlock within the structure, and those structures exhibit very interesting properties. Now let me, this is the a single formula I have in this presentation, by the way. It gives you the survival probability of a structure under a stress sigma. Following the so-called Weibull statistics, this survival probability not only depends on the stress, but also on the volume of the part we are talking about, or structural member we are talking about. And that means that by decreasing the volume, you increase the survival probability. And you know, of course, that if a vase like this one breaks, it breaks very easily if you drop it. But if you try to break the segments, it is much harder. They are smaller, and so their survival probability is higher. There is a lot of mechanics behind that. If you have a structure assembled from elements and have interfaces here, a crack propagating from one element and hitting the interface just produces delamination here, but the crack will be blunted here, and it will propagate in some other way, but much more complicated way, along much more involved path, and that means a higher energy dissipation. So you would get an increased resistance to crack propagation, to failure. Now, we want small elements, so we want to fragment a structure or segment a structure in small elements, but we want to be able to assemble a structure from these elements. So we came up with a design which we called osteomorphic blocks, osteo from bone, obviously, and morphic relating to their structure. And these blocks have a shape which at the interfaces has a concave or convex surfaces. If you match these surfaces in a way indicated here, you need a bit of geometric or space imagination to see what happens here. But you can see that you can produce a structure like that, a planar structure or a corner-like structure like that. And if you try to push an element out of this structure by just applying a load normally to this plate, you cannot do that because the matching surfaces of the neighbors will prevent its movement. 3 of the neighbors will obstruct the movement in one direction, 3 others in the other direction. That is one family of what we call interlocking blocks. They're interlocked in the structure topologically or geometrically, but we can also have another family of blocks which are convex polyhedra, like tetrahedra here. And if you stack them in this way, it can be shown that you cannot move out an element out of the structure apart from the elements at the periphery. So you have to fix them somehow. But those which have the right neighborhood are arrested within the structure. So some of the structures are shown here: corner structure, column structure, and this is the shape of the block. So it is thick on this side, entire structures, entire houses out of these elements. Now, if you deform a brittle plate, its force deflection profile, and the loading is here, a concentrated load here. The monolithic plate would respond in a very catastrophic way. It will deform, and then without a warning, it will just break without any plasticity, without any ductility. If, by contrast, you look at our assembly of interlocking blocks, the response will be like that. So you have actually a huge ductility, you have a huge bendability of the structure. You can see it here, actually. The block to which the load was applied has moved quite a lot, almost by the well, half of its thickness, and yet it is still within the structure. It is arrested by its neighbors. The load-bearing capability dropped, but the entire work done, the entire energy that such a structure is capable of absorbing, that is the area below this curve, is obviously much larger than in this case. So these are structures which can absorb energy. They can also resist catastrophic failure, as demonstrated here. Catastrophic failure of a monolithic plate, as opposed to very localized failure of a plate consisting of interlocked blocks. The rest of the structure is actually intact, so that even if you lost some of the elements of the structure, say by projectiles hitting the structure, it still can survive until, sorry, I wanted to show you the result that demonstrate that you need to fail about quarter of the blocks before percolating damage of the structure occurs. And that is, of course, a very high tolerance to local failure. You can also combine elements of entirely different nature, soft and hard, stiff and compliant, those with high thermal conductivity and those with low thermal conductivity, and so on. So you can combine functions of materials in one integral structure. And in fact, you can you have an unlimited variability of the functional properties that you can achieve, because you can mix materials in any proportion within a structure like that. And notably, if you want to disassemble the structure, you can recycle those blocks. Those which didn't fail can be reused again in a different structure. There are quite a number of geometries of the elementary blocks that permit this topological interlocking. In fact, all 5 Platonic bodies give us examples of such interlocking. So the cubes, octahedra, icosahedra, dodecahedra, along with the tetrahedra, do possess this property. You only have to know how you stack them together so that you get this full interlocking in the structure. Now, my colleague at the A&M University in Texas, Vinaya Krishnamurti and Urban Ackerman, have come up with a huge zoo of other interlockable structures. I just wanted to show a couple. These are the so-called Delaunay lofts. They also have some woven structures like fabrics, which also possess this full interlocking capability. So there are quite interesting ways of moving from here into wearable fabrics, into hollow structures which you can feel with, say, phase-changed materials which would absorb energy during the day and release it during the night, so that you can use that in construction, in arid areas, in extraterrestrial construction, and so on. So there could be quite a number of applications. Now, among the structures that have been tested so far, in terms of energy absorption and the maximum load that they can carry, the octahedra have shown the best combination of properties under both quasi-static and impact dynamic loading. But the space of such geometries is huge, so lots of things are unexplored, and so there is a lot of room for fantasy of the designer to further develop these structures. Oh, this is the picture that shows that you need 25%, nearly 25% of damaged blocks in the structure before you reach a percolation limit, when the fracture would propagate across the entire structure. Sound absorption. If you look at structures like this, and compare the sound absorption coefficient of the base material, which was just a particular ceramic, and then look at the sound absorption coefficient of the structure made from these osteomorphic blocks, you can see a pretty good result, almost 70% of sound absorption in the audible part of the sound spectrum. And that is just by segmenting the material into these interlockable blocks. If you further try and tune the internal structure of the material, like introducing porosity or various levels of porosity, and that is what we tried to do, you can even further increase the sound absorption to nearly 100%, or say 95%. So again, there's not only the impact energy absorption capability of the structure, but also the sound absorption that can be improved by segmentation. You can also give the structure responsiveness to external stimuli. In this case, we just passed shape memory wires through the material, loaded this material, stopped the loading device. There was a bit of load or stress relaxation, and then we passed an electric current through those shape memory wires. That is, we heated the wires instantaneously, or almost instantaneously, and there was a drop in the load here, which came as a response to that. And if you switch the current off, you get back to the continuation of this load relaxation line. We also demonstrated for some polymeric materials that you can have this sort of responsiveness to heating by the electric current. So that gives the possibility of using such structures for actuation or for sensing purposes as well. Now, the last thing I want to demonstrate, and again, we go back to biomimetics and borrow this idea of combining hard and soft matter within a structure. We were able to improve both the strength and the ductility of the material. And we looked into the structure of nacre of a mollusk shell, a baloney shell, which this is a classical example already of a structure consisting of, well, basically ceramic platelets, calcium carbonate platelets, which are hexagonal, like hexagonal tablets, stacked together in this way. And in between, there are layers, and also between them, layers of proteins, soft matter. Now, our osteomorphic blocks resemble those platelets if we look at the projection from the top of the structure. You can see a similar structure. So we took ceramic osteomorphic blocks, and we also embedded them and or interleaved them with some resin, with a soft polymer. And look what happened. If we take the base material from which the structures were produced and deform them under concentrated load, just loading in the middle, you get catastrophic fracturing, catastrophic failure. And this is this curve here, which we already saw. Load elongation or load displacement, an elastic behavior, high load bearing capability, but a catastrophic failure in this fashion that we see here. If we look at the interlock structure, but without the resin, just our ceramic osteomorphic blocks assembled in this way, you have a response like that, a lower maximum load, yet some compliance, some ductility, some bendability of the structure. You get a pretty large plastic strain, or pseudo-plastic strain. Now, with this resin added, you get this type of behavior. And that is amazing. You get an improvement of strength, so you almost reach the monolithic plate properties, and you get a huge ductility. And with that, I really want to finish by just perhaps saying that we have a very interesting combination of properties which we achieve by very simple means. We have full reusability, a very easy assembly and disassembly of the material, full recyclability, and many options for combining different functionalities within a single structure. I think with this, I should finish by thanking you for your patience. I think I talked longer than I was allowed to, but I hope it was not too boring for you. Thank you.
Yes, thank you very much, Mr. Estrin, for this interesting talk today. Thank you for everyone who was listening to, and now we can open up for discussion and your questions.
Well, the very principle is size independent. The blocks could be huge, they could be small, just depending on the manufacturability of them. But yes, of course, there are different aspects due to the size effect. First, if there is some error in the size, that error accumulates as you have more and more elements in the structure. So there's one thing that is perhaps a bit dangerous and needs being explored. Also, say if you have a structure which is confined by a frame, and say it's a horizontal structure, just a layer structure, under the own weight of the structure, it will collapse as you increase the size. Apart from that, to be honest, we didn't explore the size effect in any systematic way. But yeah, there should be some effects, because we have a complex interaction between volume and surface, and the surface conditions are changing during the loading process. And this interplay has not been investigated. It's a very good question, because the answer demonstrates that it's different to the turbulence in fluids, where there is a strong rate dependence. Here it is not. It is not, at least not a significant rate dependence. It's really a matter of the strain that you impart on the structure. And the occurrence of this turbulence depends critically on the difference in the stiffness of the soft and hard layer. So it is not driven, it's not a Kelvin Helmholtz turbulence, which we know from liquids.
Thank you.
But you can know, so Professor Estrin will stay at his health institute till the end of July. So if you have any questions or would like to contact him, you can do that. So I would like to thank you, Professor Estrin, once again for the talk today. And thank you everyone for being with us today. I wish you everybody a very nice afternoon, and also a very nice day off tomorrow. So we'll be glad to see you at one of our next talks. So thank you.
Thank you very much. Thanks for listening, and see you soon.